Our new unit that we start today is called the dynamics. Our last unit, kinematics, was the study of motion. But you remember we said the study of motion without regard to what caused that motion. In other words, we looked at the motion itself. We didn't pay any attention to what caused that motion. Dynamics is also the study of motion, but with dynamics, we focus more on what causes the motion than the motion itself. Now, that doesn't mean we're not going to use what we learned last unit. We will. Those equations we learned last unit and those concepts we learned last unit will apply to this unit, but that's not our focus in this unit. Our focus is on what causes the motion as opposed to the motion itself. So let's define it before we go any further with it. It is the study of motion with regard to what causes the motion. In other words, it's the study of forces. Sorry, 1 second here. It's off. The writing is off, so I got to fix this. The force will be with you for the next few weeks. Let's define a couple more terms, just introductory dynamics terms, before we really get going on this unit here. Mass. Anybody remember the definition for mass? You've seen this before. You've defined it before in earlier grades. Mass is defined as, Marcos? No, it's not actually the weight of an object. Weight and mass are two different things, and we'll distinguish between those later on in the unit. Weight, your mass doesn't change anywhere in the universe. Like if you weigh 70 kilograms, you are 70 kilograms on Earth, 70 kilograms on Mars, 70 kilograms in the deepest reaches of space. Your mass is your mass. Now your weight does change depending upon where you are because it depends upon gravity. But mass doesn't depend upon gravity. It's the same everywhere. Your mass is simply a measurement of the amount of matter that you possess. You know what matter is, right? Atoms. The amount of matter that you possess is your mass. Whereas, again, Marcos, we'll talk more about weight a little bit later on, not too far off down the road, but a little bit later on in the unit. Weight it's related to mass. You are heavier, your weight is more if your mass is more, but it's not the same thing. Okay, because your weight also depends upon gravity in addition to mass. So mass is the amount of matter that something has. The units for mass would be what? Grams? If you take chemistry, you might think it's grams, right? Because you use, how many people take Chem 20? You use grams in chemistry, right? The reason you use grams in chemistry is because of scale at which you're doing things typically. In chemistry, you're doing things typically on a smaller scale than we are in physics, which means that grams are convenient. But in physics, we're typically doing things on slightly bigger scales, which means we're usually going to use kilograms for mass. We'll talk more about that later on, though, when we actually go to do calculations with mass. Another definition. We don't use this definition in this unit at all. I just want to distinguish between that mass and volume. So you know that there is a difference. Okay, the definitions are similar, but if we aren't careful, we're going to think they're the same. They're not the same. The amount of matter that something has versus volume is the amount of space that something takes up. So my mass is 70 kilograms because the amount of matter that I have is 70 kilograms. But the space that I take up is however many liters or however many meters cubed. That would be my volume. Mass is a much more important definition, a much more important term for us in this unit because that's what we do a lot of in this unit. We're studying forces, right? And force is dependent upon mass. So we clearly are going to use mass quite a lot in this unit. What about a force? That's the most important definition that we can have in this unit, right? Because that's what the unit's about, is forces. You guys have defined force before. I know you've defined it in grade 6, probably even before that. Grade 6, you did a unit on flight. And when you did flight, you learned about the lift force, the drag force, the thrust force. Remember those forces? You define force. Force is the good news is, guys, the way you define it in grade 6 isn't any different than the way we define it in Physics 20, Physics 30, or your third year university. A force it's a simple definition. A force is a push or a pull. A force is a push or a pull. That's all there is to it. Now, we can get into some pretty complicated types of forces, but in the end, what all of those forces do, complicated or non-complicated, what all of those forces do is either push something or pull something. That's it. We just talked about electric force in Physics 30 over the last couple of days, and we introduced something else with electric force today, this morning, in Physics 30. We defined force, electric force, as the push or pull due to some electric charge, right? It's a push or a pull, even in Physics 30. It doesn't get crazier. The definition is still a push or a pull. Here's another one. Let's start getting a little bit more complicated now. Inertia. You ever heard that term? Do you guys still watch Bill Nye videos in junior high school? Even though they're like 20 years old? Yeah? The beginning of Bill Nye, the science guy, in the song, it would always say, inertia is a property of matter. Yes, it is a property of matter, but that doesn't define it, right? It just tells you that inertia is a property of matter. So is a lot of things a property of matter. What's the definition for inertia? I don't care if you give me a perfect scientific definition. Does anybody know roughly what inertia is? Yep. That's actually really good. I don't really like the word ability to resist a change in motion. Let's use the word tendency. Everything has a tendency to resist a change in motion. Emily is sitting at her desk right now. She will remain sitting in her desk unless something causes her to move. It doesn't mean she's never going to move, but it does mean unless something causes her to move, she won't move. Does that make sense? A car is traveling down the road. It has a tendency to keep traveling down the road, okay, unless something causes it to not travel down the road, like friction or your brakes or another car that crashes into it. Everything wants to keep doing what it's doing unless something causes it to stop doing what it's doing. So everything has a certain tendency to maintain its current state of motion. That's what we're going to define as inertia. The tendency of an object to maintain its current state of motion. The tendency of an object to keep doing what it's doing. Now, what do you think affects that? What do you think affects the tendency of an object to keep doing what it's doing? If a car is traveling down the road, it wants to keep traveling down the road. But what would make it want to keep traveling down the road even more? An object that's at rest remains at rest. It's going to stay there forever unless something causes it to not remain at rest. But it would want to remain at rest even more if, fill in the blank. No. Forces acting on it would cause it to move, right? Inertia depends upon one thing. And that one thing is mass. Now, you guys have probably heard this one before. Sometimes it's called the law of inertia. We'll just call it Newton's first law. Newton's first law, also known as the law of inertia. I'll put that in brackets here. Clearly, it has something to do with an object maintaining its current state of motion, right? resisting a change of motion. Otherwise, it wouldn't be called the law of inertia. Newton's first law, the law of inertia, says an object at rest will remain at rest until acted upon by an unbalanced force. Now, that word unbalanced is important. We can't say an object at rest will remain at rest until acted upon by a force. Scott's desk is at rest. He's at rest right now, right? I'm going to apply a force on his desk. Not a very big force, but I'm still applying a force, right? Is his desk moving? No. An object at rest will remain at rest until acted upon by a force? No, that force didn't cause it to start moving. An object at rest will remain at rest until acted by an unbalanced force. When I push on Scott's desk, friction pushes back and the force is balanced, right? If I push a little bit harder, friction pushes back a little bit harder and the force is balanced. If I push a lot harder, then all of a sudden I have an unbalanced force. My force is bigger than friction, and now it's going to start moving. So it's going to remain at rest forever, not until acted upon by a force, but until acted upon by an unbalanced force. A force that's not canceled out by something else. Now, the second part of Newton's first law says an object in motion. Well, what's it want to do? It wants to stay in motion. It doesn't want to just stay in motion. It wants to stay in motion in a straight line. Well, it wants to keep going in a straight line forever and at a constant speed. It doesn't want to speed up. It doesn't want to slow down. It doesn't want to change direction unless it's acted upon by an, not a force, an unbalanced force. When I'm traveling in my car at 110 kilometers per hour on the highway, there's all kinds of forces acting on my car, but I'm going at 110, not speeding up, not slowing down. Why? Because the force is balanced. When forces are balanced, it just keeps doing what it's doing. If there are no forces, it keeps doing what it's doing. If the forces are unbalanced, that's when it speeds up, slows down, or changes direction. Now, another term that I want to define. This relates clearly to what we've been doing and all of these things that we've already defined. It's called equilibrium. You guys know what that word means? Like, it doesn't matter if it's in the context of physics or something else. Where have you heard that word before? Social? Okay, what does it mean in the context of social?
It's like, I remember in like grade social, and it was like, to find doing like the aspects. That's the one I remember.
Okay.
Oh yeah, to find like the equilibrium, because they were doing like blood sacrifices or something. So they were doing, so they did like a...
So they needed to find a balance. Where else have you seen it? The Aztecs, apparently in their human sacrifices, needed to find a balance. Yes, Maddie? That works. Yeah, that works. We're not going to use that term equilibrium in the context of human sacrifices, but we will use it meaning a balance in a different way. Yeah?
I mean, we use it in social, but like differently from like, not like an equilibrium.
Okay, so like a balance in the economy?
Yeah.
Okay. Yeah, like government intervention versus free market, whatever, the right balance of that. Okay. How about biology? Have you heard of biology? Chemistry? Yeah? Equilibrium means balance. Now, in the context of physics, it means a specific type of balance. We talk about balanced forces. If something's in equilibrium, forces are balanced. When all forces acting on an object balance each other out. Now, an object that's at rest, we don't necessarily need to distinguish between these types of equilibrium, but we will for just a moment here. If an object is at rest, it's in what we call static equilibrium. Forces are balanced on it. What's it want to do? What's it going to do? It's going to stay at rest, right? As long as it's in equilibrium, an object at rest will stay at rest because the forces are balanced. You need an unbalanced force to cause it to start moving. An object in motion, traveling in a straight line at a constant speed, is in, we call it translational equilibrium. It's moving equilibrium. The forces are still balanced, because if the forces weren't balanced, what would happen to it? It would speed up, or it would slow down, or it would change direction. But an object at rest that stays at rest must be in equilibrium, otherwise it would start moving. An object in motion in a straight line at a constant speed must be in equilibrium. Forces must balance, otherwise it would speed up, slow down, or change direction. In other words, it would accelerate, right? So that term equilibrium is really closely related to inertia, right? It has a tendency to remain at rest. It has a tendency to keep doing what it's doing. If it's in equilibrium, it will absolutely keep doing what it's doing because the forces are balanced. You need an unbalanced force to cause it to change its motion. Let's define one more thing that's real closely tied into what we just defined: equilibrium, unbalanced force, and so on. And then we'll wrap it up. Net force. The net anything is the total anything. My net salary, how many people have a job? A job? About half of you? If you have a job, you get a paycheck or direct deposit, but you get a pay stub. Everybody has to get a pay stub. And your pay stub identifies all of the money that you made in the week or the month or however often you get paid, and it identifies all your deductions as well. So for instance, you might have worked a certain number of hours, let's say 20 hours at $15 an hour gives you $300. But you might have also got a bonus of $20 because, you know, maybe the company you work for gives bonuses for extra special work or overtime or something like that. But they might take off $5. They may take off $5 for maybe a staff party fund, Christmas party fund or something like that. They might take off $15 for income tax, or $10 for Canada pension, or they might even, when I worked in a grocery store when I was in university, and I had to actually pay into a pension. Like, it was a unionized thing and I had to pay into a pension. I'm entitled to 37 cents a month for the rest of my life when I retire because of that pension that I got when I worked that summer. When you pay into a pension, maybe they take off $1 a month or whatever the case may be, right? My gross salary, okay, this is my gross salary. This is what they're paying me. My gross salary is $300. My net salary is all of these things added together. 300 plus 20, 320, plus -5 is 315, plus -15 is 300, plus -10 is 290, plus -1 is 289. My net salary is my total salary after adding all of the positives and all of the negatives. Make sense? The net force acting on an object is the sum of all of the forces. In other words, it's the unbalanced force, the sum of all of the forces, including direction. Say if you got a force to the right, make that positive, a force to the left, make that negative. Add all the forces together, including the positives and negatives, and that will give us the net force, the sum of all the forces acting on an object, and we're going to say include direction, i.e. positives and negatives. Now, in a couple of days, we'll actually use this term, start using this term a lot, because we'll deal with Newton's second law mathematically, which is going to involve having a net force and calculating the total force like we calculated the total salary right here.